In practice, basically no one uses the brute force method, unless they're absolutely desperate to be positive that what they have works, or they're working with a very simple system. Because with complete graphs, if you take anything more than 4 vertices, for example, if we talked about those flights from earlier where we were talking about the complete graph on 5 vertices, that would mean 5 minus 1, or 4 factorial, that is 24 comparisons. So if you went 1 more than that, we'd get over 100. And then go 2 more than that, and we're talking about multiple thousands of comparisons, which is not a reasonable amount of work, and that's in a case where we know how much work it would be. Like I said, we don't necessarily have a nice pattern for Hamiltonian paths and circuits on general graphs, so we wouldn't even know necessarily how many things we'd have to check, much less be able to check every single one of them. So, brute force, it gets you a definitely correct answer, but at the cost of taking up all of your time. So, probably don't want to rely on it too much. And instead, we have an approximate method, which is called the nearest neighbor method, where for this, what you have to do is, again, model your problem using a weighted graph, then identify the vertex that runs as your starting point. From the starting point, choose an edge with the smallest weight, then move along this to the second vertex. From the second vertex, choose an edge with the smallest weight that does not lead back to one you've already been to, then move on to that third vertex. Then continue building your circuit following that pattern basically one at a time until you hit all of them, and then from the last vertex, return to your starting point. Where this is a process that is called sometimes a greedy algorithm because it has to go through every single case, every single part of the problem to be able to get all of the things you need, and because it's a little bit random in how it works, especially with the cases of ties, it's not always guaranteed to get the very best, but it will usually give a good approximate, and even though it is still a lot of work, it's almost always a lot less work than brute force. So this is what you'd see more likely in practice of a complex example, of a real-world example that has more than 4 things to it. And that's what we're going to finish our section here looking at. So for the flights seen earlier, we're going to use the nearest neighbor method to approximate an optimal solution, assuming Seattle is the starting point. So when we're looking at this organization here, we have that from Seattle, we would go to LA as our cheapest option because our options are LA for $70, Chicago for $145, Atlanta for $140, or Dallas for $120, so we're going to go to LA. Then at LA, the cheapest option we have that is not going directly back to Seattle is going to Chicago for $100. Then at Chicago, we don't want to go to LA or Seattle. Our options are either, well, Dallas for $165 or Atlanta there for $75. And then when we get to Atlanta, because Atlanta is cheaper, we have just Dallas for $85 because we're basically out of options at that point. And then at Dallas, we've been everywhere else. We've got to end up back home at Seattle for $120. So following that nearest neighbor method, going through the nearest one of each of our options, we would end up having the total cost there is $70 plus $100 plus $75 plus $85 plus $120 for a total of $450. And that would be at least our approximate best solution. Might be the best, probably the best, looks like it should be the best. But if you wanted to be sure, you'd have to go through all 24 of those potential cases, and we do have better things to do with our time. I like graph theory, but that's not the most exciting job in the world as far as I'm concerned, even though I do like it. So, that's what we got here for 14.3. We've got one last section left where we're going to be looking at another special kind of graph called a tree next.